final limit. So this is what stopped people in the 60s to believe in the standard model of the electroweak sector of the standard model, because this Pauli Villars or some other things did not give it seemed not possible to regularize it and extract finite gauge invariant results. Now a better way, of course, is dimensional regularization, which is most popular in perturbation theory. And just to sketch how this works in principle, is first we can rewrite this term in this form. So this is simply an identity, right? It's an auxiliary parameter lambda that we integrate from 0 to infinity, and then we get back to this term. So here we haven't done anything dangerous, just rewriting this. And now we can combine this with the momentum integral and exchange the order of the integrals. That is not dangerous either. This lambda m squared term can be anticipated, and the momentum integral is only here. And now if we assume this lambda to be finite, actually this is an integral that can easily be done. This is simply a d-dimensional Gauss integral. The result is given here. And we still have this exponential factor. And now we still have to do this lambda integral. And we see from this structure, we can, let's say, do a substitution, call this term here lambda prime. And then we have here some power of lambda prime up to some constant factors. We get here a gamma function of, according to the definition, 1 minus the exponent here. So we have a gamma function given here. So this is the general, the easiest definition of a gamma function is given here. And if we just, let's say, if we perform integration by parts, we can transform it into this one and say if s is an integer, a positive integer, then this gives us s to the minus 1 factorial. Now if s is negative or complex, then we cannot actually do this integration by parts. But what we can do is we look at this equation here. Gamma s is s minus 1, gamma s minus 1. Also we take this as a definition of gamma s minus 1 is taken by gamma s divided by s minus 1, and then we use this to define gamma s minus 1. So to start with these integrals in the half plane of, this is the complex plane for s. Here we have an explicit definition, and now we can always perform one jump by 1 unit to the left, and in this way define it all over the complex plane. But this is an unique analytic continuation. It's not shown here, but one can show it. The only points where this fails is if we would divide by 0 here. So if we start with gamma of 1, then we would need to divide by 0, so this fails. So here we have a hole which fails, and then of course minus 1 also fails, minus 2 also fails, and so on. So we have a definition all over the complex plane up to this discrete holes for the negative for 0 and the negative integers. But then the regularization is then simply to say, well, we move a little bit away from this, okay, in this case we are interested in a gamma of minus 1, which is exactly such a hole where it is not defined. Of course, must be the case because the integral is divergent, but we can move a little bit away from it in any direction of the complex plane. Let's say we work at s minus 1 minus epsilon 1/2, so move it a little bit away. Then it is well defined. This corresponds to mathematically to 4 plus epsilon dimensions. Do all the calculation, and at the end take this epsilon to 0. This is a very successful regularization scheme. Okay, it is not, even within perturbation theory, there are also some tricks to it. In particular, okay, what we will discuss in the last lecture is particularly this matrix gamma 5, the product of the Dirac matrices in all the directions 1 to d, let's say in the Euclidean space, or 0 to d minus 1 in Minkowski space. Now, what shall we do with that in 4 plus epsilon dimensions? That's not obvious. What the Toft-Veltman suggested in 72 is basically use the same gamma 5 as in 4 dimensions, but here we do not have a unique analytic continuation in epsilon. So we can here still handle this on the regularized level in different ways. and if one then always gets the same result in the finite limit epsilon to 0, this is not so clear. So here, and the one loop level is not problematic, but the multi-loop level, one has in fact problems with that. And this is the matrix that we use to define chiral symmetry. We will discuss the problems with chiral symmetry on the lattice extensively. Here I just mentioned that not only the lattice, also dimensional regularization has a conceptual ambiguity with the chiral symmetry. So, okay, as you know, that colleagues here at CPPF, when they were still in La Plata, Argentina, they first suggested this method of dimensional regularization and demonstrated in particular gauge invariance in QED already. And okay, I suppose this story is well known at CPPF, that then Topf Feldman got famous and got up to the Nobel Prize with that. Of course, they have done more. They have worked out the whole electroweak sector of the standard model. But okay, we have written this now recently as a popular science article, which if somebody wants to read the story, it's here in Physics Today in February edition of this year. Or if somebody prefers a Spanish version, we have written earlier as a simpler text in English and Spanish this year. Physics Today is much more ambitious, so they have even involved a professional historian to check every detail and so on. So this is entertaining to read. So at this point, okay, as we get to the end, we have introduced quantum field theory in the functional integral formalism completely. But so far we only discussed scalar fields with self-interactions because no other fields are around. Now the next step will then be to introduce also gauge fields and then fermions. And once we put it together, we have QCD and we can see what the results and what the status is. So this I will leave for next time. So even if you're familiar with gauge fields, but the funny thing is that we can introduce gauge fields directly on the lattice, on the regularized form, so that we have something which is manifestly gauge invariant on the regularized level. This has been achieved in continuum only with this formulation, which was before considered almost impossible. You will see that on the lattice actually it's very easy to do. It's, we can do everything from scratch with gauge variables, and everything is gauge invariant by default. But okay, they always have advantages and disadvantages, but at least gauge invariance is quite easy to implement, and it is the most important symmetry, of course, in field theory. This must be exact, otherwise you're not doing gauge theory. Yeah? That's, okay, it was recently, last week in this workshop for Robert Ubatuba, and I couldn't believe it. There was again confusion about this point that people break it a little bit and so on. If it's broken, then it's gone. And if a gauge transformation, you can make a small breaking, a large breaking, and once it is broken, then you're doing something else, but you're not doing gauge theory anymore. So if we say, okay, gauge theory is very successful in describing nature, so we should stay with this concept, and we would recommend to stay with this concept. Of course, somebody can try something different, but if we want to talk about photons and gluons and so on, then we need gauge theory, we need exact gauge symmetry, and it needs to be preserved on the regularized level. We cannot break it a little and hope for it to come back later. This works for other symmetries like rotation symmetry. This we can break a little, it's a global symmetry that we can break a little and it safely comes back in the continuum limit. This was shown rigorously by Semantic and his people, but if we break gauge symmetry at the regularized level, then the game is lost already. So that's very important to show how this works, and then fermions are of course a subject to discuss afterwards. Good. Okay, have you made any progress with the simulations? Or? Okay, maybe we can look at it in a moment just to see if there's some particular point that stops you, then we can see maybe what to do about. And I think there was also the set of analytical questions. Is there? I thought that the last lecture is for short, will maximally be 1 hour. So if somebody has a solution, either of a simulation or an analytic question, I would be most happy if he could then present as he likes on the Blackboard or even with a PowerPoint what he has done. It doesn't need to be where you can have typos and so on, but just to see what has been done. So you can pick any of the questions that you like, and if you have a solution.
I wasn't in the last lecture, so I didn't know. I performed no exercise.
no, I was talking. I think the gentleman behind you, he has. Yes, so maybe you can show me what you have done, and then we can present it to the public at later stage.
What the problems?
Yes.
Solve the problems.
Yes, if you have solved any of them, then it would be nice if you show the solution, maybe at the end of the last lecture. Yeah.
Yes.
Any of the problems that you need, that is find convenient to. Okay, there are a lot of physics, Grassmann algebra, this I will go the next time, but okay, actually they're very entertaining. Okay, let's stop at this point.
A little question, both them.
Yeah.
You have to rely on finite dimensional lattices because computer has limits.
Yes.
And for example, I don't know, 5 cross 5 cross 5 cross 5.
It's a bit small, yes. No,
Yeah.
no, you're right. Not only the lattice spacing must be finite, but also the lattice volume must be finite.
Yeah,
now, so what we can afford, let's say in QCD, is something like, let's say 32 to the 3 times 64. We usually take the Euclidean time direction longer because then we can measure the decay of this correlations better. So we have more time to, more points to detect this decay. And then we can tune the parameters so that maybe this lattice spacing corresponds physically maybe to 0.1 Fermi. Then it's not, the discretization is not so bad, and at the same time the total volume is more than 3 Fermi. It's also not so bad because, let's say, the correlation length is the inverse Bayer mass is around 1 Fermi. So if we have this clearly longer than the correlation length, then the finite size effects are reasonably suppressed and the lattice spacing effects are suppressed. So we have a number of points which are affordable, and we have to arrange it such that both the lattice spacing is usually the worst problem. The finite size effects tend to decay exponentially in the volume, so they are usually not so bad.
That's my point. You mentioned that this finite size of the lattice can account for systematic errors.
Mm-hmm.
How do you keep them under control in the end?
Yes. I mean, you're performing measurements at finite lattice spacing at a finite volume, and then you have to perform you repeat these measurements. Maybe one thing you can do is keep the lattice spacing fixed and extend the volume, or keep the volume fixed and reduce the lattice spacing, and you need different extrapolations. So actually you cannot just read off, you need different, and quite often you need even a third extrapolation, so there's a tricky industry behind it. It's a combination of different extrapolations to get really to the physical point. And to start with, you already have some uncertainty, statistical uncertainty in the measurements, and then in addition you get uncertainty due to the extrapolation. But well, there are elaborated methods how to estimate the uncertainty. So if, let's say we have different points. Here, let's say we have a fixed volume, then we have a lattice spacing here A, and we measure something like, let's say, m rho over m time. Deal better with only with dimensionless numbers. Then we have something like this. And usually theory tells us also how the behavior is, if this should be proportional to A squared or proportional to A. This we can elaborate theoretically, and then we have such points, and let's say if it is A squared, then there is such a fit, and say, okay, the fit has some additional uncertainties also up to this. This is then the result in the continuum limit at some finite volume, and then we vary the volume and take the results in the continuum limit each time. And okay, this is then, let's say, 1 over volume, and extrapolate this to infinite volume, then the uncertainty is again getting a bit larger. But nowadays, with all the computer power available, we'll show next time that the summed up uncertainty, let's say, to compute a proper mass, if you have all the uncertainties included, is about 3%, so it's really not so bad anymore.
About how much percent?
3%. Yeah?
3.
So we can start only with gluons, let them interact with valence quarks, let them interact by gluons. It generates all the C quarks, all this mess of coupled gluons. You don't understand that, but what is going on, because it's a really dense mess of this virtual particle stress which emerges, but then we can measure the proton mass and we get the right value of energy up to about an uncertainty of 3%, and it is inside the phenomenological value. So this is quite recent. This is over the last 5 years or so that we are able to do that. Okay, we have different collaborations around the world that are able to do that, and now we see that really QCD predicts a proton mass correctly. This is until very recently, this was actually not really known if this comes out correctly.
It's rather impressive.
Yeah, that's okay. It's a combined effect of having faster computers, but not only that, it's also better algorithms, better control over these extrapolations and so on, and better lattice formulations to maintain the symmetries in a better form and so on. There's a lot of different things coming together, but it's really, we can say that the hadron spectrum can be reproduced from first principles of QCD up to a couple of percent of uncertainty, so that's with all the extrapolations included. Okay, I will show examples for this next time without going into technical details, but just give the overview of what is the status of hadron physics for me.
So we're going to speak about that.
Yeah, next time I will show that.
That will be nice.
Yeah, yes. After introducing H fields and solions, but then we have everything to have QCD formulated, and then I show typical results of what is the status.
All right.
Okay, good. Thank you for your patience.